Hello, everyone. Welcome to Year 10 webinar. Technically, it's webinar number 2 because the first one unfortunately got cancelled. But I'm going to call it webinar 3. Yeah, because I've numerated them and decided not to change the numbering system. Okay. And today we're going to talk about density and hydrostatics. This is the first assignment on physics. This is the entrance assignment. And I will be going through some very similar questions to the assignment and some less similar. I will also be talking a little bit on theory of hydrostatics, but in general, this webinar is designed to help you with is to do the first assignment effectively. And if you do well on the first assignment, you can join COMPOS and you will get a tutor. And you will have, in addition to my webinars, which happen once every 2 weeks, you will have a weekly webinar in small groups with the same tutor every time. The tutor would normally be a student from Oxford or from another UK university, and yeah, they will help you out with the remaining of assignments. So I'm going to share my screen, and I will answer the questions as we go along. Apologies, I do see some questions, but I don't want to start with them. Okay, so I'm going to share my screen, and I am recording. Yes, I am recording. Sharing my screen. And perfect. Okay. I would want to start with a question of the day, and hopefully by the end of this session, you would be able to answer this question correctly. What is heavier, 1 kilogram of iron or 1 kilogram of wood? So have a think about this question. It's not as simple as it looks. Well, yes, I see some replies in the Q&A, but they are both incorrect. Okay, so there is a correct answer to this. Well, I mean, okay, depending on how you define things. When we say heavier, what do we mean by heavier? When we say heavier, we mean which is easier to lift, probably, right? So which requires less force to lift. Because, well, some things are really heavy, but they're really easy to lift. So yeah. Anyways, then this book. I mean, this book changed me. It's called Physics for Entertainment or Physics is Fun in other translations. It's a very old physics book, and but even so, I found this book when I was 13 years old. I literally found it in the toilet of the place of the apartment we rented that was a long time ago, and I started reading it. And when I read it, I thought, oh wow, I want to study this. This is the thing I really want to study. So even though it's a very old book, you might find it very interesting, and if you do find it interesting, it might change the way you look at things. So I do recommend download. You can download this book, or because it's past it's I think it's like 1929 or something. So you can download it. Anyways, yes, the whiteboard I'm using, you have access to it. And there are 2 ways you can access this whiteboard. So first of all, you can just click the link. And here we are. Or if you go to our website and you click on webinars and Year 10 whiteboard. If you click on Year 10 whiteboard, that takes you to this particular whiteboard, where you can follow everything I do, and you can always look back at previous sessions. And the first thing I want to talk about is using algebra in physics. So we tend to use a lot of algebra in physics, more than you would typically use in GCSE or even A level. We tend to leave calculations to the very end. What do I mean? So let's have a look at this problem. So the moral of the story: do not substitute your numerical values until you get a final answer. Okay. All right. It's not a prescriptive. Try not to substitute. Okay. So what do we mean by that? Well, let's have a look. A bag of sand is dropped from the roof of the 30-meter tall building. How much does the sand heat up? How much the sand heats up when it hits the ground? Okay, so what on earth is going on? We don't need to. I'm not requiring you to know everything here, but we have a bag of sand. It falls to the ground. It hits the ground, and it gets warmer. Well, why does it get warmer? Well, because when it falls, it has kinetic energy, and when it hits the ground, that kinetic energy turns into thermal energy. So we have an energy conversion. We have gravitational potential energy to kinetic energy. As it falls, it accelerates, and then it has right. And then it turns into thermal. So effectively, what it means is that the temperature of the sand and the surroundings slightly increases. Now we need a few values. Well, first of all, we need the specific heat capacity of sand. So the thermal energy, we know that eventually we have gravitational potential energy turning into thermal energy. And you have two formulas. Gravitational potential energy can be calculated using mass times gravitational field strength times the height of a building, in this particular case, the building. And the thermal energy, Q, can be calculated using mass times C times the change in temperature. Now, C for sand, C, the specific heat capacity for sand, I believe it's 800. Well, let's look it up. Specific heat capacity of sand. 0. Let's say 0.8. So 800. 800 joules per kilogram per degree Celsius. It doesn't matter. It's not important what this is. The problem is that when you use your GCSE approach, when you use your typical approach that you tend to use in school, you would start doing, okay, gravitational potential energy. Gravitational potential energy is mass times gravity times height. Well, I know gravity is 10. I know that G is 10 newtons per kilogram. I know the height, but I don't know the mass. I'm unable to calculate GPE because I don't know the mass. I have no mass, so I cannot calculate GPE. So I'm already stuck. I'm already stuck when I'm trying to do the numbers. So it's question mark times 10 times 30. Okay, of course, some of you would say, well, use an unknown variable. Yes, you could use an unknown variable. You could say, like, it's m times 10 times 30. But it's quite unsettling. Like, I'm trying to use this approach, but I cannot do the calculation because I don't have enough numbers. I don't have enough data. And the same for thermal energy. When you try to calculate the thermal energy, you have so many unknowns. The only thing you do know, so the thermal energy, is mass times the specific heat capacity times the change in temperature. So the only thing you know is this. Everything else is unknown. So how are you going to do this? And that's why we use the algebraic approach to this problem. So we say, well, if we know that GPE is converted to thermal, we can assume 100% conversion. We can assume that all of GPE goes into thermal. So we can say that MGH is equal to MC delta T. And immediately you see you can divide both sides by M, and M cancels out. Now you want to find the change in temperature, so you want to find delta T. So you divide both equations by delta T, oh, by C, sorry. We divide by C. And you get an equation, GH divided by C equals delta T. We write it in delta T equals G times H divided by C. I have the answer. This is the answer I'm interested in. And this is the answer you will be tested on when you write your answer, your solution. We want to see something like this. And then, yes, of course, you only need to substitute, of course. So delta T, now G is 10, and 10 newtons per kilogram. H is 30 meters times 30 meters, and divided by C, which is specific heat capacity, which is 800 joules per kilogram per degree Celsius. Okay, now kilograms cancel. And then you have Newton meters, so you have 300 Newton meters divided by 800 joules per degree Celsius. Now, Newton times meter is actually a joule, so joules cancel, and this Celsius goes on top. So it's 300 divided by 800, 300 divided by 800, which is 0.375 degrees Celsius. So you see what I did? I found the answer in as an algebraic expression, and then I substituted the values to get the final answer. And even if you mess this thing up completely, you'll still get full marks. Well, at least at COMPOS, you will. If you see a correct expression without, and the numbers are messed up, you'll still normally receive full mark, because that's the important bit. So hopefully that makes sense. Let's look at another reason why you would use the algebraic approach is units consistency. Because let's say you write an equation. Force equals, oh no, so let's say mass times acceleration equals the gravitational force plus normal reaction force. And then somebody tells you that the reaction force is 80 newtons and the mass is 3 kilograms. So you get 3, so you decide to substitute 3a equals fg plus 80. Now, you know that acceleration is measured in, and you have fg equals 3a minus 80. So what's the problem with this expression? Well, the problem with this expression is the following. Acceleration is meters per second squared, and this is newtons. So it looks like you're trying add meters per second squared in newtons, which is not possible. You can't do that. Of course, the correct way to write this would be 3 kilograms A minus 80. And then you don't have this problem, 80 newtons, because kilogram times meters per second squared is a newton. But it's very difficult if you make a mistake. It would be very obvious where you made a mistake if you use algebra. If you start putting in numbers, it is less obvious where you made the mistake. I hope that makes sense, and I hope you'll see what I mean. Like in the near future, if you don't fully understand what I mean. But I'll see. As we go along, I might show you something like that. But a very common mistake would be, I don't know, G plus 3 then times M equals, I don't know, 17. It's like, how could you add G and 3? 3 is then just a number, and G is a unit. It is newtons per kilogram. Why are you adding newtons per kilogram and unitless numbers? So that's the kind of thing I'm talking about. Anyways, I'm going off topic. Let's go back. Problem 2. A skydiver of mass m is falling at terminal velocity. Assuming the coefficient of air resistance k is known, find the speed of the skydiver. This would be a typical question. You have no numbers at all, no numbers whatsoever. Okay, so what do you do? Well, you say you have a skydiver, and you know that the coefficient of air resistance is no. So we do need a model for air resistance. We will say that F of air resistance is a constant multiplied by the speed, right? So you have the force of the air resistance, and you have the gravitational force, which is mass times gravity, mg. Now, because it's at terminal velocity, that means the forces are balanced. Terminal velocity means forces are balanced. And therefore, F of air resistance must be equal to mg. And we know that the air resistance is kV. kV equals mg. And you need the speed, so v is mg divided by k. So to find the speed of the skydiver, you just need to know the mass of the skydiver, assuming you know k. And this is an answer. This is a valid answer to a physics question. If you look at, if I open any university physics book, most of the answers look like this. It's an algebraic expression. So answer is an algebraic expression made up of values assumed to be known. So in the skydiver of mass m, so mass m, that means m is known. Coefficient of air resistance known. So k is known. And g is known. So you know m, you know g, you can calculate the speed. That's it. Okay, cool. Now let's go to our actual topic, and the actual topic is liquid. We're talking about density and yeah, density and pressure. Sorry, density and hydrostatics. Yes, so this is hydrostatic pressure. Pressure increases with depth. You probably know that if you try to dive into a swimming pool at the depth of about 2 meters, your ears start to hurt. If you go down to 3 meters, the pain is quite significant. I think I've been up to 4 meters, and that was almost intolerable just for me, but maybe you're different. But definitely 4 meters, I felt my ears really, really popping, and it was very hard to hold my breath. So yeah, if you go into the water, the deeper you go, the more the pressure. And you can see that on this experiment, on this very common experiment. The pressure of the water the pressure pushing the water out of the nozzle is bigger because it is a greater depth. Right, so this is the depth, this is the depth, and this is the depth. So more depth means more pressure. And let's look at some interesting stuff. So vet under pressure. Okay, let's switch off the atmosphere. And I want you to predict. So I'm going to put a pressure meter on the on here, and I'm going to put a pressure meter here. Where do you think, and I'm going to put a pressure meter here, where do you think I have more pressure? Oh, I should have prepared a vote. Wow, I got so many answers. How do you cancel on Newton? Newton times meter is a joule. There's a question like that. Well, the pressure here, and the pressure here are exactly the same. It doesn't matter what's on top. The only thing that matters is the depth. And if I reduce the depth, I reduce the pressure. And if the breath depth is 0, there's no pressure at all. Okay. And if you go less deep, of course, you have less pressure. So the deeper you go, the more pressure there is. Now, the pressure can be calculated using the formula. Pressure is density of the liquid times the gravitational field strength times the depth, or H. I kind of want to prove this formula. How much time do I have? And how many problems do I have left? Okay. All right. Yes, I'll prove this formula, even though I've done this in one of the previous webinars. So pressure is, we know that the pressure is force divided by area. That's a given. So imagine you have a column of water. This is a column of water. We know that the density of water, density, is mass divided by volume. And volume, if this is the area, this is the cross-sectional area, and this is the height, we know that the volume is area times the height. It's a cuboid. It's a cuboid. So it's the volume of a cuboid. So putting these together, we can, from here, we can rearrange mass is equal to density times volume. And we know that volume is AH, so that's density times A times H. Okay. Now, the force on the bottom, the force is equal to the weight of the water. And the weight, we know it's mass times the gravitational field strength, mass times gravity. And we know that mass is rho AH, so that's rho AHG. And finally, we have pressure is equal to force divided by area, which is rho AHG, so force, divided by A. A cancels, and I get rho GH. So that's how we get the formula for pressure inside a fluid, well, inside a liquid, as a matter of fact, because we don't normally use this equation for gases, because gases don't have the same density. Right? If you go to the bottom of the deepest sea, which is the Mariana Trench, which is 11 kilometers, I believe, the density of the water would be almost the same as the density of water at the surface. So the density of water does not change with depth, doesn't really change with depth. And the reason for that is because liquids are incompressible. You cannot compress a liquid. It's almost impossible. Uh, and if we're talking about a gas, the air at the surface of the Earth is much denser than the air high up in the mountains. So high up in the mountains, the density of the air is much lower. Apologies. Okay, so yeah, so the examples. Pressure increases with depth. Well, okay. Why things float? And derive the formula for Archimedes for. Well, we already know. Yeah, let's look at a swimming pool. So swimming pool. Oh, actually, no, we don't need a swimming pool. We have this lovely, lovely FET simulation. So let's put some water in, and we can see that the pressure is more and more and more. Okay. So it allows only 4 pressure meters. So we can see that pressure increases. Basically, I like to say, well, if you're thinking of the wall of the container, then the pressure gets bigger, bigger, and bigger the deeper you go. So this is the pressure. So here on the bottom, it's going to be the same everywhere. And then you have a similar situation here. So decreasing pressure as you go up. Okay. So you have very high pressure on the bottom and increasing pressure on the side. And this, we will need this. So let's look at this boat. You can see that some of the boat is underwater, of course. And we know that pressure increases with depth. So at the top, there's less pressure. And the deeper you go, the more pressure there is. So the water pushes the boat, in this case, it pushes it up. And you can see that there is a resultant force. All these pressures, they add up to one total force, which is going up, which is called the buoyant force or Archimedes force. F, Archimedes force, buoyancy. I prefer Archimedes because I don't know how to spell buoyancy. Buoyancy. Let's assume it's spelled like that. Buoyancy. Buoyancy. Oh, I think that's right. And of course, there's the gravitational force. So there's weight, and the weight is equal to the Archimedes force. That's why the boat floats. Let's look at a hot air balloon. Now, a hot air balloon is inside air. It's in our atmosphere. We actually live on the bottom of an ocean called the atmosphere. If you think about it, it's not technically called an ocean, but it actually is. It surrounds the whole of the earth and it pushes on things. The air pushes on things. And the deeper you go into the air, the higher that pushing force. So the air pushes on the balloon, but the deeper it is, the lower it is, the higher that pressure. Just like inside water, there is more pressure on the lower parts of the balloon, hot air balloon. And that's why hot air balloons fly, because the pressure on this bottom is more, and you have a bigger force going, which is called the Archimedes force or buoyant force. And of course, there's the gravitational force, but hot air balloons are quite heavy, so they have the weight, quite a large weight. But again, these two forces are equal. So you can see that there's an upthrust force, which is the Archimedes force, which is the buoyancy force, and there's the weight. So these are balanced. Now, if you're thinking of a fish is fully submerged underwater, and there's a upthrust force. So why is there an upthrust force? Well, for the same reason. Of course, because the lower part of the fish is deeper in the water than the top part of the fish. And that means that the pressure on the top part side of the fish is lower than the pressure on the bottom side of the fish. I'm exaggerating here, but you get the point. The deeper you go, the more pressure there is. So if I place a fish into this tank, the pressure on the lower side of the fish is going to be bigger than the pressure on the top side of the fish. And that's why fishes are pushed upwards to counteract their weight. Of course, the weight pulls them down, but the upthrust pulls them up and they remain at constant depth, just like a submarine. Okay, so now let's work out a formula for the Archimedes force. So imagine you have a cuboid inside water. So you have a swimming, and you have a cuboid. Okay. You have a cuboid, and the cross-sectional area is A. So A is the area, and the height is H. And then density of the object. That's the density of the material that it is made of, and density of the water, of the liquid. Let's not say water, liquid. Liquid, density of the liquid. All right. So we know that at the top we have pressure. So let's say it is at a depth D. So we have pressure at the top, and we have pressure at the bottom. And we know that the pressure on the bottom is pressure at the bottom. Okay. Now, we know that the pressure at the top is rho g d, where d is the depth, is the distance from the top surface of the water to the top of the column, and the pressure at the bottom is rho g d plus h, because it is deeper inside the water. So this is like I don't know. Let's say it's a brick. It's not important what it is, but it's an object. It's an object submerged into water. Okay. Now, the force on the top side of the brick. So force is pressure times area. Force is pressure times area. So the force on the top side of the brick is equal to the liquid pressure on the top side of the brick is rho GD multiplied by the cross-sectional area. And the force on the bottom is rho G D plus H times A. Now the difference, the upthrust or the Archimedes force, is the force on the bottom minus the force on the top. And that is rho G D plus H A minus rho G D A. You probably notice how much algebra I'm using, right? So I'm barely using any numbers at all. I'm opening the brackets, rho G D A plus rho G H A minus rho G D A. Rho G D A cancels, and I'm left with rho G H A. But remember that for a cuboid, the volume is rho G H. The volume is HA. It's the height times the cross-sectional area. So the upthrust is rho GV. And that's the formula for the upthrust force. And it's quite fascinating. Okay. Archimedes force is the upthrust. Right, so there's a few questions. Is this the same with planes? No, planes fly because there is a lift force. Airplane, so airplane, airplane. Um, so when an airplane flies, so there are four forces. So there's a thrust force. Thrust, that's the engine. There's the drag force, that's the air resistance. Drag. There's the weight force, weight, and then there's the lift force. The wings provide the lift. And for a plane to fly, thrust must equal to drag, and the lift must equal to weight. In almost all circumstances, except when the plane is taking off. When the plane is taking off, the thrust is bigger than the drag. But in other cases, the thrust and drag are the same or very close, or they're very, or they're very close, right? Right. So that's I think this question is answered. In theory, can I jump in a bottomless liquid tank and float at some point? No, vice versa. You would be squeezed, and all the air in your body would be squeezed. Your density would increase, and you would actually sink better. So no. Um, the you still have pressure on the top, which also increases, and the pressure on the bottom also increases, and the difference is the same. So at any depth, you would be just as buoyant, except if you go really deep, then you'll be squashed into a smaller version of you, and then your density would increase. Can the Archimedes force be also considered an upthrust? It is upthrust. So what is the container? What if the container is not a cuboid? Would the proof still work? You would need to use integration for a proof like that. But yes, it would still work, but it just would be a much more complicated derivation using integrals. Can we access this whiteboard at all time? Yes, you can access this whiteboard at all time. They will be the same if they are the same depth. Who is the same depth? I'm not sure what that refers to. Sorry. Third one. I don't know what that means. Yes, Newton times meter is and joule is the same thing because work is force times distance. Work is measured in joules, force is measured in newtons, and distance is measured in meters. So Newton meter is the same as a joule. Okay. The first Q is thermal energy, so it's not that important. Yes. In most questions, yes, try to answer as algebraic expressions, but if it's not possible, of course not. I mean, be reasonable, right? It's not that black and white. Okay. Does the tank matter about your shape? No, the formula is universal, but I can't prove it for any shape. It works for any shape. Uh, any shape works for any shape. And interestingly, that rho GV is actually a something else is rho GV, because if you remove that block and you replace it with water, so imagine you remove the block and replace with water. So the volume of the water, so the mass of the water. So imagine you replace the block with water. The mass of the water is density times the volume, and the weight is the mass times gravitational field strength. So it's rho v g, which is the same, rho gv. So actually, upthrust is the weight. So this means that upthrust is equal to the weight of displaced water, displaced liquid, which is really important. The upthrust force is the weight of the displaced fluid. So if you let's think about this hot air balloon. If you remove the hot air balloon and replace that hot air balloon with air, the Archimedes force is exactly the weight of the air removed. of the air that has been, well, displaced by the hot air balloon. If you take this ship, the weight of the water displaced by the ship. So when the ship is placed on the water, some of the water goes sideways, right? So the ship displaces water. And it says, so the ship displaces water, and the weight of that displaced water is exactly the upthrust force. Okay. Now let's move on to problem 5. So this is a question where we will do calculations. I just want you to be confident in dealing with these things. So you have a brick. You have a brick, and this has a density, and it has volume, and it has an area. Of course, you could calculate the area. So the mass of the brick. So A, mass is density times volume. And therefore, we need the volume first. Volume V is, well, it's width times length times height, which is 0.1025. I'm doing it in meters, of course, times length 0.215 times should have left more space for myself, times 0.073 meters, and that is 1025 times 1025 times 215 times 0.073, which is 0.000161 cubic meters. That's the volume of the brick. So the mass M is equal to density times volume. So density is 1,600 kilograms per cubic meter, multiplied by the volume, which is 0.000161. So I've got an extra zero. Okay, and it's cubic meters. Cubic meters cancel out. And I've got kilograms, so times 1,600, which is 2.57 kilograms, which is very reasonable for a brick. Okay. But you see how I still use the formula, and I only used well, I did find the volume first. Okay. Anyways, B, I found the volume, and then I did mass is density times volume. The weight of the brick. Well, we know that the weight is mass times gravity, so it's 2.57 kilograms multiplied by 10, because G is 10 newtons per kilogram. Kilogram cancel, and we got 25.7 newtons. C, normal reaction from the floor. Normal reaction from the floor. So we know that if the brick is on the floor, there's the gravitational force, mg, and there's the normal reaction force, So normal reaction force has to be equal to mg because the brick is stationary, which is equal to 25.7 newtons. Right. So if you put something on the floor, the reaction force is exactly the same as the weight. Well, not exactly, depending on the medium, because if you put it in water, as we will see, D, normal reaction from the floor if the brick is submerged in water. So So this is the brick, and it's inside the water. And now we have three forces. We have the weight, we have the upthrust force, and we have the normal reaction force. And in this case, the upthrust force plus the normal reaction, so the floor is pushing the brick and the water is pushing the brick, is equal to the weight. So the normal reaction force is the weight minus the upthrust force. So we know the weight, which is mg, and the upthrust force is rho gv. So rho gv, and we can now calculate it. So mg, we already have the calculation. It's 25.7 newtons minus rho. Density of water is 1,000. Density of water is 1,000 kilograms per cubic meter. 1,000 kilograms per cubic meter multiplied by G, which is 10 newtons per kilogram, and multiplied by the volume, which we already know, is 0.00161. 0.00161 meters cubed. So you can see meters cubed cancel, kilograms cancel, and we are left with newtons. So we go 25.7 minus 10,000, so 16.1, which is 9.6 newtons. So interestingly, the weight of the brick, well, the normal reaction from between the brick and the floor is actually 9.6. That means if you were trying to lift the brick, you don't need 25.7 newtons. To lift the brick in water, you only need 9.6 because the upthrust is helping you. So to lift brick in air, you need 25.7 newtons. Same as normal. To lift brick in water, you only need 9.6 newtons. So that's why stuff is lighter in water. I don't know if you ever tried this. Take something heavy, put it in the water, it's easier to lift. That actually touches on the question of the day, which is heavier, a kilogram of iron or a kilogram of, was it wood? Wood, I think. Yes. All right. Finally, F. How would the brick behave if we put it into mercury? Oh, that's an interesting one. Well, actually, it would float. Bricks float in mercury. And it would float better than wood does in water. So F. It would float. And it would float in such a way because the density of mercury is 13.7. Density of mercury. Density of mercury. 13.6 is 13,600 kilograms per cubic meter. The density of brick is 1,600 kilograms per cubic meter. So it's almost 10 times. Almost 10 times. So that means that if you put a brick in the mercury, only 10% under mercury. Can you say under mercury? Under surface. So it would float better. A brick would float better in mercury than it than wood floats in water, because if you put wood in water, 80% of the wood is underwater and 20% is above. And let's see, anvil. Well, this was in anvil in mercury. So here you are. Well, this video this video is linked in the assignment, so you can see an anvil, a really big metal anvil floating in mercury, and it actually floats better than wood in water. Okay. Now the question is, how much force would you need to sink a there was a question like this: how much force do you need to sink a brick in mercury? How much force to sink a brick in mercury? Well, you would need to consider the following. So here, the brick is floating. So there's the weight and there's the upthrust. And these are two equal. Weight is equal to upthrust. But if you want it to sink, so the brick has to be underwater. So the weight is the same. The upthrust is much bigger now because it's here it's only 10% underwater. Here it's completely underwater. So you need a pushing force. So an F, and that's the force that you are trying to find, push. And because the brick is balanced, then the upthrust must equal to weight plus the pushing force. So the pushing force is upthrust minus the weight. So pushing force, the upthrust is rho GV, rho G times volume, minus the weight of the brick, which we already know. So rho GV, so it's 13,600 times 10 times the volume, 0.00161, minus 25.7, sorry, minus 25.7. And that will give you 13,600 times 10 times 0.00161 is 218 minus 25.7, 193.26 newtons. So you need almost what, 8 times the force, right? So to actually put a brick on surface of the mercury and push it down, that force is 8 times more than the force you need to actually lift the brick. So pretty cool. Anyways, because we have a question which is very similar to that, so I hope that helps. Okay, problem 6. A hollow tube of diameter D is placed into water. A disk of height h and diameter d is placed tightly at the bottom of the tube. Density of the disk is greater than the density of the water. Find the depth at which the disk detaches from the tube. Right, so what on earth is going on here? Okay, so a hollow tube of diameter d, so we diameter d. A disk of height h and diameter d, so we have the big diameter d, is placed tightly at the bottom of the tube. So inside there's air. Inside this air. And actually, I just remembered I've prepared a quick demo. Just give me a moment. All right. Yes, sorry. Stop sharing. So this is a quick demo. You've probably seen this before. So I've got a glass of water, and if I take a piece of paper, this piece of paper, and I put it on top like this, and I turn it over, the water doesn't spill. So the atmospheric pressure holds the water, and okay, just quickly take a snapshot. Okay, so yeah, that's what's going on, and I can take this paper off, and it's just a regular glass of water. And okay, now I'm going to post this here. I'm going to share my screen again. And so what's going on here is that the water pushes on the paper on the bottom. So the paper becomes slightly bent out of shape. So there's this, and that means that this surface of the water also bends slightly. And that means that the pressure outside and pressure in, because the water level slightly decreases, pressure in is slightly less than the pressure out. So the pressure of the atmosphere, the atmospheric pressure, pushes on the paper from pressure out, and not allowing the water to spill, basically. So in a way, something similar is going on here, because the pressure, the pressure here pushing the pushing the, this is the air, because this is connected to the atmosphere. So this is the atmospheric pressure. And here on the bottom, you have a liquid pressure, which is actually the depth is the atmospheric pressure plus rho g plus the liquid pressure. So let's call it P bottom. So pressure on the bottom is the atmospheric pressure plus rho g and the depth. And the depth is h plus h. Okay. So now we look at this little thing. And we can see that we have mg, mg, well, so is the gravitational force. Then we have the pressure from the bottom times. Okay, so pressure on the bottom times the area of the bottom. So pressure bottom times the area, that's the force. So the upwards pressure, F pressure up. And then the force of the pressure from the top. And here we have two sections. We have a section which is with a higher pressure, and we have a section with an atmospheric pressure. So we have higher pressure here, we have a lower pressure in the middle, and when we have higher pressure here. So we have force of pressure down. And this is going to be quite complicated, but hopefully that makes sense. So force of pressure up is equal to mg times plus force of pressure down. Pressure up is pressure on the bottom, pressure bottom times the area equals mg. Well, we don't know m. We have density of the disk. So we know the diameter, and we know the diameter, we know the height. So it's going to be pi d squared over 4, that's the area, multiplied by small h, that's the volume, times the density of the disk, and times g. Okay, plus the pressure down. So the pressure down is the atmospheric pressure multiplied by pi d small squared over 4 plus PA plus rho G capital H, that's the pressure on this side, multiplied by the area, which is pi d big squared over 4 minus pi d squared over 4. All right. Okay, the area is smaller. It's the area of the big disk minus the area of the small disk. All right, it's getting complicated very quickly, but hopefully that makes sense. So pressure on the bottom is PA plus rho G H plus H times A times A. I'm opening the brackets, so I'm putting this in, equals pi d squared over 4h rho disk g plus rho atmosphere pi d squared over 4. And A is, it's the big A, so it's pi d squared over 4, pi d squared over 4, plus PA pi big D squared over 4 minus PA pi small d squared over 4 plus rho GH pi d squared over 4 minus rho GH pi small d squared over 4. And now we get to substitute, so simplify. So pi d squared PA. So this cancels with this. This cancels with this. Oh, that's very nice. Rho GH. Rho GH. Pi d squared over 4. Rho GH pi d squared over 4. Yes, that cancels. And oh, this doesn't cancel. Okay, all right, let's write it out. Rho G small h pi big D squared over 4 equals pi D squared over 4 h density of the disk G plus minus rho G big H pi D squared over 4. So pi cancels, 4 cancels, G cancels. Okay, we get rho H D squared equals rho D H small h big D squared minus rho big H D squared. And finally, we just need, what do we need? We need the depth, which a depth H. We need capital H. Okay, so rho H D squared equals rho D H D squared minus rho H D squared. And then we divide everything by rho D squared. So H, simplifying this, H D squared, open bracket, rho density of the disk minus density of the liquid, divided by rho D squared. Right. I apologize if some of my explanations weren't clear, and I apologize for jumping in for so complicated equations. But in reality, this is more like this is the kind of stuff you would normally do in at COMPOS'. You have everything is in algebraic terms. So you start from the first principle. So you start with a simple diagram, then you write down the equation, and then you just do some maths effectively, and you find H. So you can see H is an expression in terms of known values, because all of these are known values. And finally, we get to the interesting part, the question of the day. What is heavier, 1 kilogram of iron or 1 kilogram of wood? Now, remember when I said if you put a brick into water, it's easier to lift. Well, that's also true for if you put things in air, they're easier to lift than without air. Because let's have a look. So let's go in water. You have a brick, and this is the lifting force. Lifting force. and there is the weight, and there is the upthrust force. So the lifting force plus upthrust is equal to the weight. In other words, the lifting force is equal to the weight of the brick minus the upthrust. Remember, we had this expression. But the upthrust force is equal to density of the fluid times the gravitational force times the volume. So in air, density of air is 1.3 kilograms per cubic meter. So the upthrust of a brick in air is 1.3 multiplied by 10 multiplied by 0.00161. 1.3 times 10 times 0.00161, which is 0.02 newtons. So the upthrust force, so a brick is 0.02 newtons easier to lift in air compared to vacuum. Because in vacuum, there's no upthrust force. In water, it's significantly easier. But in air, it's a tiny fraction. It's a tiny bit easier to lift. So now, look, if you have iron, if you have a piece of iron, then the lifting force is the weight, which is 1 kilogram, 10 newtons, minus the upthrust. And for wood, so wood and iron, but wood has a bigger volume. So the lifting force is the weight minus the upthrust. But upthrust is density of the air times the volume of the object times the gravitational field. And obviously wood has a bigger volume. So volume of the wood is bigger than the volume of the iron. And therefore the upthrust on the wood is greater than the upthrust on the iron, ever so slightly, of course. So, and that means the lifting force on the iron is greater than the lifting force on the wood, ever so slightly, because it's the weight, which is the same. They have the same weight. We know it's 1 kilogram, 1 kilogram and 1 kilogram. But the upthrust on the wood is slightly more because it is submerged in air and the air pushes up. And it's like a hot air balloon, but a very, very small one with a very teeny weeny upthrust force. So yes, wood is easier to lift. Cool. I'll run through your questions. Apologies, I've been ignoring them right. When is the deadline for the test and how do we publish? Instructions will be sent to you by email. And the deadline, I think it's 5th of October. Yes, 5th of October. How do you have to do the same working out as in examples? No. Well, your explanation, your solution should be clear, right? So we don't. If you just give the answer, you mightn't get 0 marks just if you don't have an explanation of your solution. All solutions must be well. You should explain your solutions. Well, how do we submit answers for the assignments? Yes, instructions will be sent by email. Are you allowed to ask ChatGPT for an example question for a topic or let it explain a topic to you? I did well. No, not for the original assignment, for the first assignment. You can do that for the consequent assignments, but not for these. You can do some research. Well, yeah, if you explain a topic if you want to explain a topic, I don't see a problem with that. Solving a problem with AI is not acceptable. That makes sense. Maybe not. This is my first time. So okay, right. They both weigh 1 kilogram. True. Well, they both weigh 10 newtons, right? Because mass and weight is not the same. They both weigh 10 newtons, but that's not the question. The question which is easier to lift, which is heavier. They're the same. Okay, but same. Both weigh the same, but the iron block is more dense. True. Same heaviness. Wood takes up a larger space. Yes. Okay. How do you answer the well, that's a question from the assignment. Yeah, so you just need a calculation of volume. So just unit conversions. If thrust and drag are the same, how does the plane move forward and it's not stationary? Well, it would if the plane were stationary, there would be no drag at all. Why would there be drag if the plane was stationary? As you increase the force, the forwards force, the plane goes faster, faster, and faster. And as the plane goes faster, that increases the drag. Of course, while the plane is accelerating, the thrust is slightly more than the drag, but it's only significantly more when it's taking off. But once the plane is in the air, uh, pretty much they're very close. Okay, thrust might be slightly more when it's accelerating, but when it's traveling at constant speed, they have to be exactly the same. I hope that answers your question, Rebecca. What would happen if you were in a fluid with a non-uniform density gradient, such as salt water, with varying temperature? How does the variation in fluid density affect your buoyant force and submerging? Was Archimedes' principle modified to accurately predict the object's equilibrium position and stability? Well, you would have a much more complicated formula. No, let's put it that way. You would it would be rather than rho gh, because we're assuming that rho is constant, but let's say density is changing, so it would be rho h gh, and to find the full pressure, you would integrate, of course, from 0 to the depth rho hg dh. So this would be the correct expression for the pressure, assuming you know how pressure changes. Pressure at depth h. Sorry, it's rho h g dh. And so rho h is the function of pressure, of density. Okay. Does the tank matter about your shape? Yeah, so no, the formula doesn't. In my explanation, I only used one shape, but it can be proved for any shape. Okay, sorry, that's a bit 1.19 times more massive means times 1.19. Yes, not 2.19. 1.19. Since pressure increases with depth, would that mean that in the case of the plane, the pressure determines the weight and lift? Well, for a plane, the pressure on the wings, because the plane is moving, there's a dynamic pressure, right? It's not static pressure. With an hot air balloon, it's a aerostat. It's a static force on the balloon that's providing the upthrust. With an airplane, it's a lift force which is a dynamic force, a dynamic pressure. Okay, does pressure equals upthrust? No, pressure times area is equal to the force. Pressure times area equals to the force. Pressure on the up, so pressure on the top, so pressure on the bottom minus the pressure on the top. So the pressure differential times the area is equal to upthrust. If that makes sense. Other questions including atmospheric pressure. Sometimes you need to consider atmospheric pressure, sometimes you don't. So yeah, it depends on the question, of course. Question 4, join math test, writing. Question 4A. I'm sorry, we'll have a math webinar in 2 weeks. Can you please ask that question about maths? Sorry, I don't have time to open the maths assignment. Apologies. Please. Maths webinar. What does U and the N stand for? Upthrust and normal reaction. Okay. How do I do the homework after downloading? So you will have instructions will be sent to you by email. Is the normal reaction force the same as the weight force? Oh, because it's stationary. Like, if something is on my hand, it is stationary. So there's a weight force down and up, a normal reaction force up, and they are the same. Well, almost the same because there's a tiny weeny upthrust force. Remember? So there's actually a little bit air is pushing my phone up. If my phone was, I don't know, 20 times bigger, it might float in the air like a hot air balloon. But it's yeah. Stationary because it is stationary. It is crucial to understand. Wow, questions are adding. Oh, is it crucial to understand prove these questions? Remember the equation. Just remember the equation. That's fine. Do you have to do the same working out as examples? Well, it's some level of yes, I've answered that question. How do I join the Google Classroom? Why would you join the Google Classroom? Sorry, I'm not sure. You don't need to. Like, I'm not aware that you need to join any Google Classroom at this time. You can join a Google Classroom once you're unsuccessful to the main program. So in November, we will send links to join the Google Classroom for those who don't want to do COMPOS, don't want to do the whole COMPOS. They want to just do the light version of COMPOS. Do we need a full explanation showing your working is good enough? As long as it's clear how you got to the answer, right? So your solution has to go, this is what we have, this is the equations I use, and this is how I got the answer. This should be clear. It doesn't have to be, it doesn't have to include excruciating details, just some explanation. Should this still apply to if the equation in the webinar passed my ability or it's harder than the first assignment? Should I say if the equations in this webinar pass my ability or harder than the it's slightly with the things I was doing, it was slightly harder than the first assignment. We have 1 or 2 hard questions in the assignment, but we expect, well, more than 50% of the assignment completed is very good. Okay, so we certainly have people on our program starting with 50%. 50% have a completed assignment. So no, if you can't do this kind of algebra, it's fine. You're not expected to do this. Would the drag not? I'm taught physics by a chemistry teacher. I qualify for the additional support group. I don't do support groups. I don't know, honestly. You can email Compos and ask that question. Compos email, please. Compos at physics. Compos at physics.ox.ac.uk. Would drag not equally slow it down on the wood, making it more equal? Drag, I'm not sure what drag you're referring to. Drag is only when you move. You can't have drag if you're not moving. Theoretically, the force from the due atmospheric pressure and the upthrust equals to the weight of an object can technically stay at the same height in the atmosphere. The force due to atmospheric pressure and the upthrust equals the weight of an object. Can it technically stay at the same height in the atmosphere? Yeah, like a hot air balloon can stay afloat at a certain height without going up or down. Right? If lifting plus upthrust is weight. The upthrust on the wood is bigger. Sorry, the upthrust on the wood is bigger, so the lifting force has to be smaller. So, yes. So the lifting force is smaller, but the upthrust is bigger, so it's equal to the same value. So the upthrust helps you to lift things. When we submit answers, do we submit parts separately or different photos on the same photos? Each question would be a separate photo, but instructions will be sent to you by email, so don't worry about it. Are these exact same questions in the video webinars too? We have different questions in different webinars. So you can look at past webinars and you'll find some other questions. And thank you for your help. Always, you're welcome. 6 minus 7, 6, 7. What's 6 minus 7? I'm not sure what that means. If lifting plus upthrust, okay, I've answered that question. How do I upload the homework? Well, instructions will be sent to you by email. How do you upload the homework? Instructions will be sent by email. We don't need to join a Google Classroom at this time, so don't worry. Where do I send the assignment? Okay, I've answered that. Do you have to show your work for every question? Well, some work, of course, yes. I mean, so show your reasoning. You don't have to show like meticulous working. Just explain explain your point of view. They just show, you might get marks for that. Just showing us step by step working with no writing is good enough. No writing. I'm not sure what that means. How can you show step by step without any writing? Just explain. It can be equations written in sequence is an explanation, right? Of course. Where are we supposed to submit the assignment because I finished the maths? We will send you instructions. Are there only the harder types of questions which will be in the test? No, the test has various levels of difficulty. So we have easy at the start. We got about 60% of them are quite easy, and 40% are slightly harder. So yeah. In problem 5 in the physics says pressure of the column is equal to the atmospheric pressure. What part of the column does it mean? At the bottom, talking about at the bottom. Yeah, at the bottom of the column. So how deep do you need to go to? I think that's the question. Right. How many students have applied for COMPOS this year? I think it's 4,000, but you must know that about half of them don't do anything. Okay, so we normally have, if we have 4,000 applicants, 2,000 people actually do the work, and 1,000 will be accepted. So chances about 50%. Okay. 1 in 2 gets in. The actual webinar is harder than the first assignment. Some of the questions are, some of the questions are not. So I mean, the questions I did with the problem 5, that would be a medium difficulty problem. Okay, the rest of the questions are slightly hard. So this webinar was slightly on the harder side. If you go back to my previous webinars on the same topic, you'll see that they are easier. So yeah, could you theoretically get 100% in maths and only 10 and 20% in physics and still get in? Probably not. You would need at least 40% in physics. I think that's the criteria. If you get 100% in maths and 40% in physics, you'll probably get in, but not guaranteed, of course. So aim for 50 and 50. Well, no, aim for more, but okay. Right, I think it's time to finish because stuff to do. So I hope that was useful. Please go back and watch my previous webinars on the same topic if you are still confused. As I said, today's webinar was slightly harder than normal. And all right, so I'll see you all in 2 weeks' time on the 29th of September for some maths. You're welcome.